Hello Gators, we'll be exploring types of discontinuities and defining continuity at a point. Informally, a function is continuous when it can be drawn without lifting a pencil. Roughly, continuous means connected. Types of discontinuities. The first one is called removable when we have a hole in the graph. When we have a vertical asymptote and the graph wants to follow that asymptote, we call it an infinite discontinuity. When we have a graph that has a gap in it, we call that jump discontinuity. Which graphs are continuous or discontinuous at point A? Name the discontinuity. Stop the screencast and see what you can do. And here are the answers. Notice graph 3 and 4 are removable discontinuity. We have a hole in the graph. We have a hole in the graph. We also have a value, but they're not the same. Notice 5 has continuous. Notice that the value and the limit look like they're the same. Another kind of discontinuity is called oscillating discontinuity. That occurs very rarely, but this is the way it looks. For each function, identify the type of each discontinuity and where it is located. I went ahead and factored, and after I factored, I noticed that two of the factors, one in the numerator and one in the denominator, are exactly the same. That's an indication of a hole. So over here at x equal to 2, we have a hole, which means that it's going to be removable discontinuity. The second factor that's in the denominator is going to be our vertical asymptote, and a vertical asymptote means the graph wants to follow it vertically up or down, and that would be called infinite discontinuity. Over here on G, I went ahead and factored. It's a difference of two squares, and again I have another difference of two squares, which I go ahead and factor. I find that I do have a factor in the numerator and denominator. This is the whole, and so this will be removable. And we have a factor here that cannot be equal to 0. That'll be our vertical asymptote, and that'll be infinite discontinuity. The other factor that we don't have to worry about because any x can be put into there and it'll still be defined. We have tangent of 2x. The 2 is going to affect the period. The period will now be half as much. Normally the period is pi. Now the period will be pi halves. These were all the places where we're going to have this vertical asymptote. So the answer is it's discontinuous at pi fourths, 3 pi fourths, 5 pi fourths, 7 pi fourths, and this is all because it's an infinite discontinuity. Number 4 is a parabola, and a parabola is well behaved, it's nice and smooth, so this function is continuous. There will not be any place where we have a point of discontinuity. Here is the formal definition. Something is continuous at x equals c if and only if you have a y value there, you have a limit as x approaches c, and the limit and the value are equal to each other. Continuity on an interval means that f is continuous on all of the x values, and it meets this definition for all those x values. At the endpoints of a closed interval, you will only have one-sided limits that need to equal the function value. Most of the techniques of calculus require that functions be continuous, so this is a really important topic. A function is continuous if you can draw it in one motion without picking up your pencil. A function is continuous at a point if the limit is the same as the value of the function, and that's what I'm trying to say here. The limit is equal to the value of the function. Here is the formal definition of continuity. The limit exists, the value exists, and they equal each other. Let's take a look at this first. This is not continuous at x equal to 2, not continuous, and the reason is there is no value. not continuous because f of 2 does not exist. Now, this next graph is continuous. There aren't any values that, where the definition doesn't apply. Over here we have this gap, and this gap means we don't have a limit. So the limit as x approaches 3 of f of x does not exist, and that's why it's not continuous at 3. Over here we have the same idea. It's the same reason. The limit as x approaches 3 of f of x does not exist, and that's why it's not continuous at 3. It's continuous everywhere else, but not at 3. List all x values of discontinuity. So we're going to go ahead and follow the graph, following it, and then all of a sudden there's an interruption, and that's at x equal to 1. And this interruption is a removable discontinuity. Now let's continue drawing, and then again we have a hole here at 2, so we know this is a removable discontinuity. And then we continue, and we notice that we're following an asymptote, and this asymptote is at 3, which means it's an infinite discontinuity. And then we continue here, and at 5 we have to hop up, there's a gap, and then we continue, and that will be a jump discontinuity. So where is it continuous? Well, it's continuous from negative infinity to negative 1, not including negative 1. Negative 1 to 2, don't include 2. 2 to 3, don't include 3. 3 to 5, and we're not going to include 5 in this interval from 3 to 5, but we are going to include the 5 when we go from 5 to infinity. So this is closed because this right here is included. State whether f of x is continuous at these x values. So at x equal to negative 1 from the left means that we're going to be using this formula, and that'll be 1 plus 2 plus 1, and that limit is 4. We're going to do it from the right hand side, and that'll be negative 1 plus 2, which is equal to 1. Notice that these two are not equal. That means a limit does not exist. So not continuous, and that's because the limit as x approaches negative 1 of f of x does not exist. All right, let's take a look at what happens at 2. At 2 on the left-hand side, this will be 2 plus 2, which is 4. And then let's apply the right-hand side. So then this will be 2 to the second, which is 4. And this tells me I do have a limit. So this limit as x approaches 2 of f of x is equal to 4. Now we have one more thing we've got to consider, and that's f of 2. Now f of 2 means right here, the equal sign right here, that means I have to use this rule, and that'll be equal to 4. Notice that the value and the limit exist, so yes, this is continuous. Let's take a look at identify the type of discontinuities, if any, and where they occur. This is a line, and this is also a line. Lines we know are continuous, but we're going to take a look at what's happening at 4. So on the left-hand side, this will be 3 times 4 plus 1, which is 13. And over here will be 4 over 2 minus 1, which is equal to 1. And you can see that the limits do not equal each other. So this is not continuous, and that's because of a jump discontinuity. Let's take a look at G, and we'll take a look at negative 1 from the left-hand side. So that'll be 1 minus 2 minus 1, which will be equal to negative 2. And then over here from the right-hand side, we're going to do negative 1 minus 1, which is negative 2. Well, this tells me I have a limit. So I do have a limit as x approaches -1 of f of x. That's equal to -2. And this should be g, not f. All right, and now what I'd like to do is like to evaluate g at -1, and g at -1 is the number 5 right here. And I can see the value and the limit do not equal to each other, so it's not continuous, and it's because of removable discontinuity. So it has a limit and it has a value, they're just not equal to each other. They're not matching. Let h be the function defined by this. What value of k would make it continuous? In order to make it continuous, the left side and the right limit have to be the same. So if I'm working with the left side, that means this rule right here. So this will be 2 take away -2 squared, and I want to set it equal to the right rule here. So that'll be 4 times -2 plus k. So this will be 2 take away 4 equals -8 plus k. And then so this will be -2 equals -8 plus k. So if we allow k to be equal to 6, then we know this will be continuous, because putting 6 here will force this limit and this limit to be exactly the same. And this is the end of the screencast.